recording so that I can talk about the other example, which is 7C, as well as the transition from invariance testing in a CFA framework to an IFA IRT framework. So I'm back in the slides here. This is lecture 7, slide 25 as a transition point. So where we've been thus far, invariance testing in CFA. So this is known as factorial invariance, measurement invariance, or measurement equivalence. All of those terms mean the same thing. The measurement invariance part is the most important. That's asking whether or not your construct is being measured the same way by your items across groups or occasions. You want to at least have partial invariance. Ideally, most of your parameters would be able to be held invariant, but if some of them need to differ, that's okay. You can let them differ and move on. Structural invariance then are real differences. Once you have evidence that it's the same trait being measured across groups or time, then structural invariance is real group or time differences that may be of theoretical interest. So when we transition into IFA, it's going to be very much the same. In IRT, though, it's a little bit different. And because of the correspondence between these two, you can really only test one or the other. IRT parameters being tested for invariance or IFA parameters being tested for invariance. So we'll talk about that in more detail. So new vocabulary. Measurement invariance is now called differential item functioning. It's the same thing though. So in IRT, measurement non-invariance is differential item functioning. So there's an inversion here. Invariance means they can be the same. Diff means they need to be different. So an item has diff. People talk about it that way when persons with equal trait amounts but from different groups have different expected item responses. And an item has non-diff if the parameters can be constrained equal, meaning that they have the same predictions regardless of what group they come in. The same rules in terms of how you would set up the model are the case here as in CFA. If you have independent groups, it would be a multiple group model where it's both groups are being estimated simultaneously but separately. Dependent groups would be part of the same analysis like we just saw for the longitudinal example. And I just want to throw out a caveat. Diff testing has been around for decades, and older methods you will still see folks refer to in the literature. I would encourage you to be wary of any approach to testing diff that involves outputting a theta as if it were a real thing and sticking it in some other model like a logistic regression. That is tautological, because in order for you to believe that that theta is accurate, you have to believe that all of the items are non-diff, and that the model fits perfectly, and that theta has no error to it, which we know is never going to be the case. So I would not recommend anything along those lines. Nowadays, we have better methods because we have better computing power. So in the IRT literature, there is terminology that goes with this that is somewhat parallel to what it is in CFA, but not entirely. So there is a term called uniform diff, which is analogous to scalar non-invariance. Instead of having intercepts, though, it's focused on the B parameters specifically. So to remind you, a B parameter is found in models for binary data or graded response models for ordinal data. That is a difficulty location. It's the point on the theta continuum where your probability of a 0 versus a 1 for binary or lower versus higher for ordinal is 0.5. So it's the amount of trait you need to endorse that item, get it right, or to move on to the next category with a probability of 0.5. So if the B parameter is different, that means an item is systematically more difficult for one group than the other, regardless of theta. So despite theta, there's something else about the groups that is related to differences in how difficult the item is. As an example, how often do you cry? We might look at invariance as a function of gender, and it could be the case that people who are in one gender might be more likely to cry or admit that they cry than another, despite the fact that crying is supposed to be an indicator of some other trait. So uniform diff then is when an item is systematically more difficult across groups. Non-uniform diff is when it's also potentially more discriminating in one group versus the other. So it works better, so to speak, in one group. And the shift in item difficulty would not be constant across the trait because of this. So A parameters and B parameters are involved in terms of the IRT side of testing diff. In this version of the model, there really isn't a thing as error variance, because in full information maximum likelihood, it's not an estimated parameter. You don't need an error variance if you have binary outcomes or ordinal outcomes because you're using the Bernoulli or multinomial distributions in which variance is not a thing. So if you're doing this in full information, you wouldn't even think about it. However, if you're doing this in limited information, WLSMV, then it is actually possible to have estimated error variances once your invariance constraints are loaded. And this gets confusing because of this distinction. I will show you how to do this, but I will warn you that in practice, the model usually breaks at this point, like when you try to test differences in error variances. It doesn't work very well. So here's a picture showing uniform diff. So I have the same item hypothetically across two different groups. Cheers. In this case, where the item is located is shifted over for the green group. So for them, like the probability at 0.5 is over here. It takes a theta of 2 to have a 50-50 shot at endorsing this item, whereas for the brown group, it only requires a theta of 1. So for whatever reason, this item is more difficult in a uniform diff. Non-uniform diff would be a picture like this where there's different A parameters and potentially different B parameters, although not necessarily. So non-uniform means the item works better in one group at its difficulty location than another. Okay, so that's the IRT side. If you're doing this on the IFA side, then what we're concerned about are the IFA versions of the parameters. So we would replace A with a factor loading, right here, and we would replace B with a threshold. And as a reminder, we can choose logit or probit link functions when we're using full information maximum likelihood. We can only have probit in WLSMV. So these things are all predicting the probit in the example I'm about to show you. So in M+, if you go through invariance testing using an IFA model, what you are testing directly are the thresholds and the loadings. It's the same premise as in CFA where we have thresholds and intercepts. Nope, no we don't. What do we have in CFA again? I'll misspeak and turn it into a teaching opportunity. What are the parameters we constrain in CFA measurement and variance again? Loadings? Yep. One more? Intercepts. And one more? Error variances. So in IFA, do we still have loadings?
Yes.
Yes, we do. Do we still have intercepts?
No.
We do not. What do we get instead? Thresholds. Do we have just one per item or more than one?
Depends.
Depends on,
The number of categories.
yeah, number of categories. So in CFA, each item has one intercept regardless of its scale that it's being measured on. In IFA, we have as many thresholds as we have categories minus 1. So if we have binary outcomes, that's 1 threshold. If we have 3 categories, that's 2, and so forth. And then error variances can become a thing once constraints are placed on the loadings and the thresholds. However, the conversion from IRT to IFA then means that if you have non-invariance for these parameters, it's specific to them and not to A and B. So here's the thing. Even if the factor loadings are invariant across groups, in the IRT A parameters will not be, because of this conversion here. So I'm on slide 31, for instance. A is the factor loading times the square root of the theta variance, or the theta standard deviation. So we've been ignoring this part in a single group model because most of the time we fix our theta variance to 1 and then loadings in A's are the same. However, in an invariance solution, we can't fix the theta variance to 1 in both groups, or we're putting in a structural constraint. So that means if the alternative group has a different theta variance, it will necessarily have a different A, even if the loading part is the same. Does that make sense? Say that again. Yeah, because of this, if the theta variance differs in the alternative group, that means even if the loading is being constrained equal across groups, A is going to be different. Likewise, even if the threshold and the loading are the same across groups, if the theta mean is different and the theta variance is different, then B is going to be different. So at this stage, you kind of have to just pick a lane as to whether you're going to test the A's and B's for invariance or you're going to test the loadings and thresholds, because you will not end up at the same place. I'm going to show you the loadings and thresholds. Ways to test diff on A's and B's are very common throughout the IRT literature. Most software packages have a way to do that, and some even have ways to automate the process so it sort of figures out what the optimal combination is. So there's a lot of resources on that if you're interested. I will show you the IFA side to be consistent with how we're talking about it in this class. So, yeah, that. One other problem that you should be aware of is what happens if your groups have different uses of the response scale. And this differs by estimator. So you can test invariance on IFA model parameters, loadings and thresholds, using full information maximum likelihood. However, you have to trick M+ into doing it by making it think it's a mixture model. It's not a mixture model. It's just hijacking the mixture model architecture in terms of the estimation. So 7D is an example of what this would look like, so you have a basis to go off of. IFA using limited information, though, has the same benefits that it did with respect to just fitting this type of model in the first place. It's much faster, particularly if you have many traits. It does assume missing data are missing completely at random. Diff test is used to do nested model comparisons, so we don't have to enter things into a spreadsheet or ask for an ANOVA call in Lavaan. We get modification indices to determine sources of non-invariance, so we can help troubleshoot that. And we could potentially test differences in residual variance once the constraints are on the loadings and thresholds. However, big caveat, if you have different response categories used across groups, you have to make them the same. So if you have a 4-point scale and one group used option 4 and the other group didn't, you got to force all those 4s to become 3s in the group that used them. They all have to match. That is true in WLSMV. There is no way around it. It will yell at you if you have different possibilities. Using full information, you can actually have differences across groups. And I do have some code that I had to work up for this if anyone's in that situation and wants to see an example. So you would have to make sure that the thresholds are still mapped in terms of which one goes with which, but otherwise it is possible to have different numbers of response categories be used across groups.
Please, can you say that again? So,
Yeah.
if I have
Go ahead.
an item that is 4 categories,
Mhm.
and for one group, they are not choosing one of the categories for,
Yes.
that is going to be problematic.
Yes, that's exactly what I'm talking about. So if you have an item that has 4 categories and one group used all 4, and another group only used the first 3, then you cannot do invariance on that item in WLSMV. It won't let you. What you would have to do is to force the 4s in the group that used it to become 3s to make them the same. You'd have to collapse the categories. And that should make you uncomfortable, specifically if you have a lot of people who've said 4, right? Because then you're just disregarding what they said. But that is what is required. That is an M+ constraint, probably for convenience more than anything else. So we'll go through the process. A scalar identification, or scalar invariance rather, is the same here. Factor variances, oh, nope, hang on, I know what I'm talking about. To start with, factor variance is fixed to 1, factor covariance is free in both groups, factor means fixed to 0 for the configural model. Then we go through the process of factor loadings, all freely estimated thresholds, all estimated, and all error variances are fixed to 1. So this is your configural invariance model. I have a note, though, here that error variances are not real things in these models. They basically become what I call a slop parameter. That is an untechnical term, but it refers to the idea of just sort of fill the gaps that are left after the constraints. Like, they're not going to hold perfectly, so whatever like little wiggle room is left over in terms of having extra loading or extra threshold contributes to make the error variances different. So this is not a thing until you have constraints. So step 1, in WLSMV at least, is we fit the baseline configural model. Then we do metric-ish. So I have, these terms are not used with IFA very often, but I think they could be. Loadings at that stage. Scalar would be thresholds. And I want to make sure you're aware that not everybody agrees on this process. So the folks that come at this from a CFA perspective would proceed through the steps in the same way that we would in those models. Loadings first, then instead of intercepts, we have thresholds, but it's the same. However, some IRT folks, as well as the people who made M+, the mutanes, in their documentation recommend constraining metric and scalar at the same time. So they recommend fixing the loadings and thresholds all to be equal at once because they're dependent on each other, is the idea. I don't think that that is useful. And in terms of what the conclusion would be, like if it fits worse, you wouldn't know, is it a loading problem or is it a threshold problem or is it both? So constraining two different types of things at the same time to me isn't as useful. I would also point out that if this had to be this way, if you had to constrain the loadings and thresholds at the same time, then uniform diff could not be a thing. Because uniform diff is when you only have different difficulties and not different slopes. And so they do make that distinction of one and not the other in that field, and so to me, it seems reasonable to have both of these things be unique possibilities. That's my perspective. I could be wrong. So the error variances step, though, is the tricky part in WLSMV because they have to be fixed to 1 to start with. In order to test whether they can be not 1, we have to release them and then fit against the constrained model where they're 1 again. So I will show you this in the example that we have, and then we have structural invariance that goes through all of that. Okay, one last thing that I want to mention. So I've talked to a couple of you about this, and I forget who all I've talked to, so I'll just say it to everyone here. All of what I've said so far is predicated on the idea that we have discrete groups, right? That there's only, two languages or 2 occasions or 2 something, right? Or 3 something or 4 something. But there is a way to test invariance for continuous covariates as well. So for instance, if you wanted to know if an item became more discriminating as children got older, and you had continuous variation in age, say from, let's say, 3 to 10 or something, what some folks might say is, well, let's cut it up, and let's say I have younger kids and older kids, right? And I might have like 3 to 6 and then 7 to 10 or something. Well, that's arbitrary. Nobody likes that. What we can do instead, though, is something called moderated nonlinear factor analysis, or the worst acronym ever, MNIFL. On the Quantitude podcast, they like to make fun of this. But apparently, it was very close to being called the MONALEFA. According to Dan Bauer, he made that up. And I vote for MONALEFA, by the way. If you can bring that back, that would have been a better acronym. So we'll go with MONALEFA in here, in their honor. But Dan Bauer is the creator of this, and here's a couple papers with him and his colleagues on it. Basically, the idea is that rather than have multiple groups and say, I have this loading or that one, you can build a linear model for each of the measurement model parameters and then estimate the contribution of continuous predictors or discrete predictors to that linear model. So for instance, if I wanted to know if an item was more discriminating as kids got older, as well as potentially more discriminating in a group that had this characteristic instead of that one, then I can put in, these are essentially regression parameters, where beta 0 would be the expected loading at the reference age and for the reference group. Beta 1L would tell you how the loading changes as a continuous function of age. Beta 2 would tell you how the loading differs by group. And then beta 3 would even allow an interaction. So that this would be the age slope within the reference group, this would be the group slope within the reference age, and then this would tell you how each of those things changes as a function of the other. Same thing with the intercepts, potentially same thing with the thresholds. So this is motivated by the world of explanatory item response models. It's the same premise. The only difference is that in their formulation, they don't have any error terms at the end in the original formulation. They may have added it since then, but each of these is assuming that the loading and the intercept is perfectly determined by this linear predictor, the same as what we do in testing group invariance, right? We have 2 loadings. There's no error to that per se. So this can be done in M+ using model constraint. I do have an example I've worked up before if anyone wants to try it. There's also an R package that will do it, which probably would be a little bit easier than writing the M+ code. So if you need to do invariance with continuous variables, this is the direction that I would suggest that you go. All right, you want to see a real example? How to do it?
So before we go, I know we've used more than 2 groups. Can we have more than 2 groups?
Yes, you can have more than 2 groups. So you would have a model statement and then a model group 2, model group 3, model group 4, like as many as you need to fill that out. I'm not sure what the upper limit is, but I think it's pretty high. If you have a lot of groups, like if you want to look at invariance across 30 countries in PISA or something like that, then I would direct you towards this instead. It's called alignment. And it's the same idea, but it's asking, rather than focusing on each group individually, it's more like a variance of the parameter across groups and trying to figure out which groups can be constrained equal. And that it uses some sort of penalty function to figure all of that stuff out. So here's the first article about it. There's a whole line of research on it. If you have lots of groups, I would go with this route instead. Okay, so I heard some false enthusiasm potentially. I don't care if it's false for starting an example. It's 3 weeks left in the semester. I will take what I can get. Y'all are happy. Y'all are here. I don't know if you're happy or not, but you're here. So we'll just go with it. I'm grateful to be talking to people and not sitting and talking to myself in my basement. But this example to me is entertaining. So I will say at the start of this, to keep in mind that this is either the same old people, activities of daily living scale. We're looking at gender invariance in this case. Now, in this data set, these people were born in the early 1900s, okay? These data were collected in like the 80s and 90s of the previous decade. So that means that within this cohort, there would have been very strong gender roles in place with respect to what people are supposed to do with their lives and how they're supposed to take care of their houses and their families and everything. So I will say that this is probably not representative of what one would find today, but I think it makes for a good example within this particular cohort. So here are the differences across men and women with respect to the frequency in each category. So this is a 4-category response format for each of these 7 items, ranging from 0 to 3. And what we're looking at is whether or not men and women differ and how we would measure their ability to live independently. So you can think about this being really important in the real world, right? If you're giving a screener instrument to try to help someone identify what kind of assistance they need, does the screener need to be different if you're trying to assess a man versus a woman? Like, that would be an important thing to know. And you can think of a lot of examples where, like, people's tendencies to display what they can do might differ as a function of some other contextual variable. So I think this has a lot of real-world implications. This is also our first try with these items in terms of them being ordinal and testing invariance, and so I've tried to help highlight some of the differences. So in this case, we have C is the item format for C for categorical. I have grouping equals, and the variable in the data set is called female, and so in this example, men are going to be the referenced instead of women. I am using WLSMV with the theta parameterization, so this corresponds to a probit link. And the first thing that I have to do is save the information from the configural invariance model so that it can be read into the next model. So every model that we fit after this, there's going to be something saved for future use, and then something used from the previous model to do a comparison against, and the results in terms of whether fit got worse will be in the output of the second model. So I have model here. This is going to stay the same the whole time. So this is the men reference group model. I have 7 loadings labeled here. I have 7 thresholds. So here is the first threshold across the 7 items. Here's the second threshold across the 7 items, and here's the third. So note that if some of your categories are not observed, you will have to adjust these lines of code. So if you try to write out 7 thresholds, but you only need 6, M+ will yell at you. So the first step to this would be to go through your frequencies and make sure that all possibilities are observed for all the groups, for all the items. The item residual variances are fixed to 1. That is a default, but I'm writing it here to make sure you're aware that that is going to be something that we're potentially going to mess with in the alternative group. And the factor is identified with a mean 0, variance 1 per usual. So for the women alternative group, the code looks exactly the same, except there's no labels. So at this stage, everything is separate with respect to the measurement model, except for the item residual variances. They have to be fixed to 1 for identification. Likewise, the factor is separately identified in the alternative group. So at this stage, the groups are not on the same scale with respect to the factor whatsoever. We're just getting an initial baseline with which to judge fit. Okay, does that make sense? All right, here's what we have. So our chi-square is significance. Chi-square contribution from each group, just eyeballing this, it looks like the women are contributing more to the chi-square than the men. So their contribution is 47, almost 48, whereas the men's is 25. However, should I use these numbers, the differences between these two numbers in particular, to infer that the model fits worse for women? Because their contribution to the chi-square is 48, whereas the contribution for men is 25. Does that mean the model fits worse in women, or am I forgetting something else? Any guesses? Fits worse in women, or could be something else?
Could be something else.
Could be something else.
Sample size.
Sample size, yeah, more people, more chi-square. And sure enough, we have only 214 men versus 420 women. So yes, keep in mind that this chi-square contribution from each group is a function of misfit and sample size. So we don't have a fair comparison to make here. RMSEA is 0.07. That is significantly higher than 0.05, but it's still within shooting distance, so that's not bad. CFI and TLI are quite happy, near 1, and SRMR is 0.02, meaning the average polychoric correlation is only off by 0.02 in this model. This is pretty good. This is pretty good fitting model. Here are the, let's see, loadings for foreshadowing the next thing here. What do you think? Do these look proportionate or disproportionate? Look, I'm going to go with dis instead of unproportionate today, for the record. Proportionate or disproportionate? Yeah, the votes from the Zoomers, disproportionate. I'd say so too, because the pattern is that for a lot of these, men are higher, but then for these, men are lower, and then for this one, men is much higher. So even though these aren't on the same scale, the fact that these do not look similar in profile means there's probably going to be a lack of invariance. So here's the solution. Note that I do not have the IRT parameters in here at all. I'm just working with thresholds and loadings. So do you remember what factor loadings mean in this context? 6 is the change in the expected probit of the higher category for every additional unit of theta. So item 1 in the men has a very strong loading, whereas that same item in the women has a loading about half the size, change of probit of 3 instead of 6. Thresholds tell us about the expected probit of the lower response, conditional on a trait of 0. They are in the direction of difficulty, meaning that higher values mean the item is harder to endorse or harder to have it. Lower values mean that their item is easier to endorse or be able to do it in this case. And residual variances are all fixed to 1, so they're printed here since I referenced that in the code as well. Okay, first step then, metric. So at this stage, I am doing 2 things in the code. Everything else is the same except for these 2 lines. So I am saving this model for the next run. So I'm calling this metric A, by the way. That's foreshadowing. It's not going to pass. And then under the analysis section, I'm saying, hey, go use the information from the previous configural model as my point of comparison. And this has to be done in this order. So it's convenient for invariance testing because it's always the most complex model, and then you simplify, simplify, simplify. That's the order in which diff test has to be applied. More complex model first, a less complex model second. So then in the men group, everything is exactly the same. In the women group, what did we change? We'll play Where's Waldo. What did we change in the code to enforce metric invariance constraints? Watch in the chat, watch in the room.
We constrain the loadings for the women to be the same as
Yep.
the men.
Here's one. So yep, we use the same labels as for the men. That makes the loadings. And then the Zoomers say variance. Yep, that's the other. So variance of the factor is still 1 for identification in the reference group. It is now estimated in the alternative group. So do not forget this step. Otherwise, you are enforcing a structural constraint as well as a measurement constraint, and it could fit worse for either reason. So how many degrees of freedom did we save?
6.
We got to vote for 6? 6 it is, because we had 7 loadings in each group before. Now we only have 7 total, so we had 7 loading constraints, but we also had to give up a factor variance, so that brings us to a net 6 parameters saved. Here is the result we care about. It is labeled as chi-square test for difference testing, as opposed to chi-square test of model fit. So the interpretation is the same for model fit. This is relative to the saturated model. How much worse than perfect are we? Chi-square test for difference testing is relative to the previous model that we specified in the diff test. So we have to know what that is to know how to interpret this. So this is me helping you. M+ is not going to print that for you. So this is the test of metric invariance, of metric against configural. Here's my 6 degrees of freedom, and here's my p-value. So good news or bad news if I want my loadings to be the same? What do you think? If I want my loadings to be the same, is this a good result or a bad result?
Good result.
Yeah, this means did not hurt the model fit, did not make it worse. Even though this is non-significant, though, I wanted to go ahead and check the modification indices to see if there's any individual parameters that are problematic. And item 3 looks like it is responsible for a good chunk of that difference. So the chi-square of 9, 7 of it is due to this one loading. So I say, I don't like that. I'm going to let it go. So 2b, the difference highlighted in yellow, I added a W for the women as the non-reference group, and at step 2b, I'm freeing item 3's loading. So I did 2 different versions of this model. You can see all of the original files in the M+ download folder. Chi-square for difference testing is relative to configural. So yes, most of our damage from our chi-square is gone. I also did a comparison against metric A using this version to see if we were headed in the right direction. And yes, freeing item 3's loading makes it significantly better. So we're going to keep it that way. So our impressions in the plot here, I thought these looked disproportionate, but 3 is the only one that it flagged, which is interesting. 1, now this looks like a huge difference, but it's in logits. So the change of a logit of 3 versus 6 actually doesn't translate into much of a difference in probability. So we have to be aware that the scale on this is a little bit wonky because of the logit transformation, or probits, excuse me. A change in probit is even bigger in that case. So what is item 3? Let me find it again. Item 3's loading in men is 3.3, and item 3's loading in women is 6. So quite a difference on that one, apparently. And item 3 is cooking. So I warned you, there's going to be some gender stereotypes in here. But what this is saying in English, cooking is much more discriminating in women as an indicator. Given the context of these data, that makes sense, because cooking would have been a skill that every woman would have had to have learned in her life. Men, maybe they know how to cook, maybe they don't, because that wouldn't have been their concern back in this era. So cooking is more discriminating in women. The rest of these were able to be constrained enough without making the model fit too bad. And overall, the model still fits pretty well. Note RMSEA is much happier with us. It was 0.07. After the metric constraints, it's all the way down to 0.05 because it's ofteness per degree of freedom remaining, and we've increased the number of degrees of freedom by 6. The variance for women is much lower than men. It's down to, it's 0.6. So women appear to be at this stage more homogeneous in their abilities on this trait relative to men. Okay. With me so far? Yeah. Now we're up to scalar, threshold time. Okay, we're going to play Where's Waldo with the code. Scalar A is what I'm saving this model as. I'm comparing it back to the partial metric invariance model where item 3's loading is free, but the rest are constrained. Now, what did I have to change in the code? This is a different one. In order to enforce scalar constraints, what did I change? Item thresholds now constrain equal by omission. Ding, ding, ding. This blank spot is what I changed. So I am taking advantage of an option within M+ that I usually don't because it's not as transparent. But if you have your model set up here, anything that is not separately referenced, that is a default parameter, such as intercepts or thresholds, will be constrained equal. So you have to write it to make it different. So if I don't write any of them, then they're all constrained equal. And it's a lot less typing than if I went ahead and labeled every single one. So I'm taking advantage of that trick. What did I have to add to my model at the same time, given that I constrained all the thresholds equal? Factor mean, ding, ding, ding. So now the latent factor is on the same scale with respect to mean and variance in both groups. They're linked together. The variances are linked together via the loadings, and the means are linked together via the thresholds. Chi-square for difference testing is significant to 4 decimal places. Wah, wah. So here's M+ trying to be helpful. I only have the output for the men group, but the same things were queued as in the women. It wants me to estimate the factor mean in men. And it says my chi-square would improve by 40 if I did that. Can I actually do that as a choice? In men, the factor mean is fixed to 0 right now as the reference group. M+ thinks I should free it instead. 1 vote for no? I vote no. Why no? Why is this not a good idea?
And you can't estimate it, right? Like you have to have it fixed in order to estimate it?
Yeah, it's an identification constraint. So if I actually took its advice, I would break the model. Now, I wouldn't say this is M+'s fault. These are modification indices. Like, they don't care if what they're suggesting makes sense or not. That's not their job. That's our job. In this case, I don't have it in this one, but what I've also seen, I think it's coming in a different one, is sometimes in these are all thresholds because they have the dollar signs in them. Sometimes it asks for intercepts to be freed as a suggestion. I'm like, I literally can't have an intercept in this model. Why are you telling me to put one in? And if I try to put one in, it will yell at me. So these suggestions you take with a grain of salt. But the largest one with respect to individual thresholds is for item 3, threshold 3 specifically. Now this one is not surprising to me because it was item 3 whose loading needed to be different. I went ahead and tried to constrain it just because I only have 7 items and I didn't want to lose one for no reason. But yeah, this is telling me that this one in particular wants to be different, as well as the first threshold for item 3. And if we look at the distribution of the item responses, the original here, The last threshold, this difference between 0, 1, 2 versus 3, this has the most information in it because most of the people are in this last category. So I would expect this threshold that differentiates the 2 from the 3 to be the one that has the most power to detect differences. This is where the people are. Down here, there's relatively few people in these lower categories, and so you're going to have a more difficult time determining whether those thresholds want to be different across groups or not. Okay, here we are. Full scalar. Yep. Okay, so item 3, given that loading wanted to be different anyway, I'm going to go ahead and free all of item 3's thresholds. That is surprisingly difficult to say. I'm going to free item 3's thresholds. I sold seashells by the seashore. How much wood would a woodchuck chuck if a woodchuck could chuck wood? I can do that one a little better. So because I wanted all of the thresholds for item 3 to be different, I wrote them down. So anything that is not written down in the alternative group code is still being constrained equal. So are we there yet? Well, now I've got a number in the 4th decimal place. I'm moving in the right direction. But nope, still worse. What's the problem? It says item 1, threshold 3. All right, add that one. Here are the differences for item 1. Actually, I should look at the ones for item 3. Let me back up a page here. So here's item 3's thresholds after we let them be different. If you had to summarize the pattern here, what would you say? What is the conclusion we would come to about item 3's thresholds in terms of how they differ across men and women?
So item 3 is easier for men.
Yeah, it looks like item 3 is easier for men. So this is the negating weirdness that we have to go through. Thresholds are not the same thing as difficulties. They are not the point of theta where 50-50 probability happens. They are the probit, in this case, of the lower response category given a theta of 0. So lower values, smaller values mean the item is easier. Higher values mean the item is more difficult. So in this case, it's way easier for women than men. This is cooking still. So what these numbers actually tell you is a probit of -8 is a very, very tiny number, right? That's a probability near 0. So at a trait level of 0, there is a near 0 probability of not being able to cook if you're a woman. If you are of average ability, you should be able to cook. That's what this is telling you. If a man is of average ability, maybe he can cook, maybe not. So a probit of 0, by the way, would give you a 50-50 probability. So these are closing in on 0 for the can-do-it threshold. Item 1, threshold 3. This last transition point is easier in men or women? Threshold 3 for item 1, what's in front of me? Easier for men or for women? For women. Yeah, what is item 1 again? Survey says? I lost it. Housework. Weaponized incompetence. That's what I think this is. Oh, I don't know how to dust, honey. I'm sorry, I can't do it. That is totally me with the lawnmower, though. I don't know how to drive our lawnmower, and I'm not going to learn. I don't know how to drive the snowblower. I don't know how to drive the lawnmower. I don't know how the rake works. I don't know how shovels work. I'm sorry, I can't. No puedo. So yes, women have an easier time doing housework than men. On to the next one. Item 2, threshold 3, wants to be different. We free that one. Same pattern, easier for women. What was item 2 again? Bed making. I would put that under housework, but apparently that is a more specific activity than housework. At that stage, we finally hit no more thresholds being individually identified, and we have overall invariance. So we had to release quite a few things to make it work. So here's the final solution for this stage, I should say. So item 3 wants to have a different loading across groups, and 2 of the 3 thresholds for item 1, 1 threshold for item 2, and all 3 thresholds for item 3 want to be different across groups. In terms of capability, at this stage, it looks like the women, as the alternative group, have a lower average score on on the factor, so they're lower by about 1/3 of the standard deviation. They are also relatively more homogeneous, so their variance is only 0.56 as opposed to a variance of 1 in the men. Okay, how are we doing? Questions so far? So the last step to this, measurement invariance, addresses these things, these residual variances. So at this stage, they all were fixed to 1, but once you place invariance constraints on both loadings and thresholds for an item, the residual variance for that item and the alternative group can then be estimated. It sounds crazy, but it can. The idea then to test it is we have to re-estimate the previous model in which we let these things be different and then compare it back to this one. Because according to diff test, the more complex model always has to be first. So we're breaking our sequence to momentarily reverse it in one direction and then we go back down. So this is what it looks like. At this stage, we estimate a new model and save the results. We do not compare it to anything yet, because this model is heading in the opposite direction. We are not constraining things, we are adding things. So this is a more complex model. What I have added are residual variances in the alternative group for items 1, 2, 4, 5, 6, and 7, but not 3. Any guesses as to why I did not try to estimate a residual variance for item 3? Why not that one?
Does it have something to do with having like separate thresholds?
Yes, indeed. It has to do with the fact that the loading is different across groups, and all 3 of its thresholds are. So a separate residual variance cannot be estimated. It's not identified. It's only identified if you have the loadings fixed equal across groups and at least one of the thresholds, I think. In this case, all 3 had to be freed. So I can ask whether allowing the residual variances to differ from 1 improves the model fit. So here's what I end up getting back. It looks like some want to be bigger, some want to be smaller. So then I have to go re-estimate the scalar invariance model in which they were all fixed equal to 1, and then compare it against that model we just estimated where they're free. So this is the one weirdness in the chain where you go the opposite direction for one step. Configural to metric saves parameters, metric to scalar saves parameters, then you hop out of the sequence, go back up a step, estimate the residual variances, and then compare it back to where scalar was where they're fixed to 1. Turns out that the result is borderline significant, so I went and tried to figure out why. Item 7 was the one that wanted to be the most different. So then I'm like, all right, then all of them can be different except for 2 and 7. I did that, 2 of them in one step, just to save time. And then we get chi-square for difference testing being non-significant. Factor variances I tried to constrain. They wanted to be different, so that's the end of the sequence. So we already know that the factor mean was different between groups. In, for example, back a few models, it's already significantly different than 0, so we know that it's different than the other group in which it is 0 for identification. So it looks like we have no structural invariance in this result. Okay, so here's the final solution then, where I've highlighted the things that want to be different. So item 3, cooking, of course, more discriminating in women. And then most of these thresholds are in the direction where they are systematically easier for women, it looks like. Yep, that one, that one, that one. Yep, I think all of those. And in terms of whatever is not the factor, item 2 has less of it for women, and item 7 has less of it for women. All right. I think we'll go over the IRT, IFA part of it next time. How's that sound? Does your cat approve? Good. Anyone else's pets approve? Because we all know that they're in charge, right? It's their world, we're just living in it. All right, then let me know if you need help with homework 5. Let us know, I should say, us and the TAs. Office hours tomorrow. Thanks for being here. Hope to see you Thursday. Stay safe. Don't get hit by any tornadoes.